Hello, good morning. Uh, I'll be continuing my discussion on philosophy of physics, and unfortunately, at certain points of time, I have to invoke some equations that and at least introduce you with some mathematical formulas. And till now, we have been talking about uh, the uh, the Einstein's general theory of relativity, and how it measures a spontaneous thing that's happening at least in solar system, that how planets move. Uh, there's not any kind of force acting on the planets. There's not any kind of force acting on the moons that are revolving around planets. Uh, it's basically this space-time curvature. It's the curvature in space-time that that leads to the motion of these planets. And in fact, in my previous talk, I talked about the Einstein's field equation. At least I moderated that equation on the board, and you could see that the various parameters that are involved in that field equation, what they represent at their basic level. I think I talked about G mu nu, then plus lambda G mu nu. This is equal to 4 pi G by C to the power of 4 and T mu nu. And this gives us the measure of space-time curvature, this tensor, and this small case of G, it gives us the shape of the curvature. And then T mu nu, it depends on the kind of problem that you are dealing with, and you can have a situation like energy and mass, and you can use it as pressure in a situation that you can explain. So this is Einstein's field equation. It's not a single equation. It's a long range of equations that boil down from this original matrix. So if I have to summarize the space-time curvature, I think it's something like that. We can think of a tensor, most probably a metric tensor, uh, uh, a metric tensor that's invoked on Einstein's field equation, and giving rise to something what's called as geodisks, and allowing these massive objects to move around some central huge mass. So it is basically the space-time curvature that that gives the motion to the planets that are moving, say, with respect to the sun, and that motion is not the result of any kind of force that we can think of is acting on the planet that's moving around the sun. What is it? It's this curvature that gives birth to this motion without invoking a force. So things in the universe might be happening in the same fashion wherever we have a dynamics like that of the solar system. Uh, the motion of the planets around those stars could be assigned to the space-time curvature, as is predicted by general theory of relativity. So there is another important outcome of general theory of relativity, what we call as gravitational lensing. So gravitational lensing is a result of the curvature. So suppose we have a star and this star is massive, and if it's a massive star, it will have more curvature in space and time around it. And the curvature can be such that it has a power. It has a power to deflect the light that's passing through the curvature of that star. And this bending of light, the bending of radiation, the bending of photons that are moving in vicinity of that star, that bending is a result of general theory of relativity. And this is what is called as gravitational lensing. I remember a course of discussion with my friends when we used to talk about the gravitational lensing. There's a story floating at ground among the students that it was all predicted by Albert Einstein, that you can have the bending of the light when the light passes through the star. This bending is a result of this space-time warping, and this is the result of space-time warping due to huge mass that's present in that domain. So if we continue talking about it, I forgot to tell you about the story. The story was that when Albert Einstein was told, he had predicted the gravitational lensing, and it was experimentally detected. It was detected while watching down the solar eclipse. So while watching down a solar eclipse, the bending of the light was experimentally verified. It was experimentally detected, and the story goes like that: Albert Einstein was told that, come on, the thing that you have predicted, that light bends when it passes through a star. He was given a chance to see the same observation through a telescope, and when he looked through that telescope, he came up with an argument. He said, I don't find anything different. Everything looks same. I'm not able to analyze the gravitational lensing. So this is how the prediction differs from what is experimentally demonstrated, at least in the framework of Albert Einstein, who was a great theoretical predictor. He could predict things that proved to be experimentally correct. Now, this is what gives us an idea about the space-time curvature, and you can see that when we talk about a black hole. So as I would like to go back to that discussion when I talked about the Chandrasekhar limit. I talked about that limit, and that limit was something that gives us an idea about the formation of a black hole, a formation of a neutron star, or a white dwarf, and this course of space-time curvature in the context of Chandrasekhar is that if you have the mass of a star, when the star is at its death, if it's more than 1.44 solar masses, then there is a probability that this star, after having supernova, may convert into a black hole, or it may convert into a neutron star. And the two classifications can be taken. If the mass is greater than 20 solar masses, then the probability of forming a black hole is maximum, and if the mass of the star is of the order of 12 to 14 solar masses, this will lead to the formation of neutron stars. So these stars, these black holes, these are very massive objects existing in universe, and their existence has been verified experimentally. And 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 what causes, what's the reasons for the formation of these massive objects is what I already talked about, is the supernova. So when a star is at the end, when the star reaches to its end, the moment its hydrogen fuel is exhausted, when all of its hydrogen is converted into the helium, and there is no further nuclear fusion taking place inside the star. And if there is no further nuclear fusion taking place inside the star, the radiations that are coming out of the core of the star, these radiations decrease. These radiations go off. So when they go off, the star collapses in its own gravitational field. Now the collapse has also to have a limit. It's not something like that the collapse will go to something where everything is concentrated at a single point, because certainly the role of quantum mechanics takes place to explain why there is no further collapse of a star. I mean, a star can convert into a neutron star, and a star can convert into a black hole, depending on the mass of the star that's linked with the star. So if you have a collapse, and that collapse makes the transformation to a neutron star, so what comes in action is the Pauli's exclusion principle. Because what exclusion principle tells us is that you cannot have two fermions who can have the same quantum state. So once you have an argument about these fermions, it becomes impossible for the collapse that's by virtue of the gravity of the star. This collapse stops at some point and gives birth to what's called as a black hole or a neutron star or a white dwarf. And the limits, I take the Chandrasekhar limits as the reference limits for the conversion of a star into a black hole, into a neutron star or a white dwarf. So we can see here in this diagram what in case of a black hole we can expect. We expect that the mass of this object is so high, the gravity is so high that the geometry of the space-time curvature for the black hole is almost leading to a singularity. And we framework this black hole in terms of this space-time curvature. And what we understand, at least from theoretical point of view, is that you have a black hole and it has a very huge curvature in its vicinity. There is a tremendous there's a tremendous power of gravity of this black hole, and that gravity leads to the curvature in space-time. And what we expect from this black hole is that even the gravity is so high, the curvature is so large that even for a particle like photon, it's impossible for a particle like photon to leave this black hole. And what we do here is we have something called as event horizon of a black hole. So we can see an event horizon, and it's impossible for a particle like photon to cross this event horizon. And at the same time, what happens at this tremendous gravity is that the time takes longer. The time takes longer. If you have a clock if you have a clock in vicinity of this event horizon, it will lead to the time dilation. So this thing can be interpreted like, so suppose there are two people, they are uh, they are in vicinity of a black hole at some safe zone. There is a safe zone, and there are two people, and one person jumps into the black hole. Now, if a person who jumps into the black hole, the time goes so slow in vicinity of the black hole, the person who is watching, the person jumping into the black hole, he will feel as if the person is floating on this black hole. It's because the time in vicinity of the black hole is dilated. It takes longer. Maybe infinitely, the person who is observing this person in vicinity of this black hole, he will be finding him. He will be finding him as if he is floating on the black hole. But the fate of that person will be harsh. The person will be gone, mashed into the black hole. But for the person who's observing this person, he will see as if the person is floating on the event horizon of the black hole. And that is because the time dilates in vicinity of black holes. And it certainly gives us an idea that the equations of Albert Einstein, what we call as field equations, what they predict is they predict something that you can have a time travel, at least in the framework of mathematical models. Now, this time travel is not the kind of time travel that we see in most of the science fiction movies, where somebody has a tendency to develop a machine and go back into the past and kill his grandfather or kill his parents. That's not the way general theory of relativity goes back, takes you back in the past.